Uh, good morning, everyone here, and then good afternoon, Professor Ravani in California. So this is our greatest pleasure to invite Professor Ravani to give the first talk at the Australasian Forum on robotics and AI for civil infrastructure. Before Professor Ravani's talk, let me introduce Professor Ravani, and his talk is about digital translation in horizontal construction. Professor Ravani is a distinguished professor of mechanical engineering at the University of California, Davis, and the co-director of the Advanced Highway Maintenance and Construction Technology Center and the UC Davis, which is funded jointly by the university and by the Department of Transportation in California. So, Professor Ravani is currently the chair of mechanical and aerospace engineering, and he has been the chair before. And his research area includes robotics and mechatronics, including applications of robotics, mechatronics, and digital technologies in intelligent transportation systems. So he has been the editor or chief editor of many ASME journals, and he has won many awards. He's a fellow of ASME, and is the past recipient of awards. So, Professor Ravani, it is really our great pleasure to invite you to give the talk, and thank you very much, and welcome to start. Yeah.
Thank you so much, and thank you for inviting me to give this talk. You know, for several years, I've been trying to apply robotics technology to improve the safety and efficiency of highway construction. So the push has been toward digital transformation of the construction and operation and maintenance of highways. So you can see now on the screen that I call it digital transformation in transportation infrastructure, but we are referring to horizontal construction. Horizontal construction is different from vertical construction. It deals with highways, bridges. Vertical construction deals with construction of buildings, and we are not discussing that. So let's see how I can move this. Oops. All right, so let's do sort of an autopsy of what do we mean by digital transformation and so forth. So if you look here on the left side, and can you guys see my cursor?
Yes, we can say yes.
Yes, so when you have a physical infrastructure, if you can somehow use some sort of LiDAR or laser scanning technique, and you develop a digital, if you develop a set of digital point cloud data, that you have, all you have done is you have created some data. And then this data by itself may not mean that much, but then the data has a lot of information in it. So you have the digital transformation is not just making the digital data. You have to be able to then form information, produce information from digital data. And one way to get information, you need to visualize the data. And once you can have visualization of the data, as well as you have extracting information from it, then you have developed knowledge of what exactly the physical infrastructure is. And then that knowledge you can use to develop a digital model. So the digital model is not just a point cloud model. It is something that has in it more than the point cloud. It has the knowledge about the physical infrastructure. If you can generate a digital model, which sometimes is called a digital twin, then you can use that model for virtual prototyping and analysis. So you can perform a lot of your design analysis engineering analysis on it before you build a physical infrastructure. So now you can look at it in the opposite direction from right to left. So if I have a digital model that is a digital twin of a physical infrastructure that I want to build, then I can do all of my design changes and do different prototype virtually, so to minimize a lot of the cost that goes with design changes during the construction. Then after that, I can go back and start the construction of the physical infrastructure. So that's one of the benefits of digital modeling and so forth. Now, in transportation, in design and development of highways, some other terminologies are used for digital transformation. One of them is called VDC, which is Virtual Design and Construction. Practically what that means, that's digital transformation of project design and delivery. So any transportation agency who is involved in design of highways, they have a design and build and delivery strategy. So if you make that from a virtual prototype, then they call that VDC. Then there is this thing that is referred to as CIM, or Civil Integrated Management. That is digital transformation at the enterprise level. Both VDC and CIM evolved from building information modeling, or BIM, BIM, from vertical construction, and now we are applying it to horizontal construction. VDC/CIM corresponds to both, and sometimes it's called BIM for infrastructure. So sometimes you see in the literature that they call it BIM, or building information modeling, but for infrastructure. So these are the elements of VDC and CIM from FHWA, Federal Highway Administration, and NCHRP. So there are different tools. These are called CIM tools. So they're modeling tools that include two-dimensional digital design tools, such as CAD systems that are two-dimensional, or three-dimensional CAD systems, or 4- and 5-dimensional tools. 4-dimensional meaning you include additional information. In addition to the geometry, you may include materials. 5-dimensional, you may include additional, in addition to materials, you would include some of the logistics for supply chain and so forth. And then there is traffic modeling and simulation tools. So these are called modeling tools. And then there are, on the other end of the spectrum, on the right-hand side, there are sensing tools. And sensing tools include use of LiDAR, either in the form of terrestrial laser scanning, or mobile laser scanning, or airborne laser scanning. There is aerial imagery using data from satellites, integration with global positioning systems, using robotic total stations. In terms of elements of the horizontal construction that's under the ground, then use of ground penetrating radar to be able to get images of what is underground. For example, in bridge construction, when you want to put pillars of the bridges, especially when you go over water. And then RFID, then real-time networks, then integrated measurement systems, and then use of drones and unmanned aerial vehicles. These are called sensing tools. And then you go in the middle, and in the middle we have data management tools. So we have to manage the data that we get. So there is project information management systems. There are asset management systems, and then of course GIS, or geographic information system. And then the use of digital signatures, so that when you have to approve projects, that one would be able to use digital signatures, and then mobile digital devices. So if you can use things like iPads or tablets at the site to be able to look at the drawings and be able to approve them, modify them, send them back through network, and update your data at the office. Now, VDC, or Virtual Design and Construction, as well as SIM, it evolved from BIM. BIM is Building Information Modeling. Now, for highways, this is called BIM for infrastructure sometimes. So let's look at BIM. So on the right-hand side, you see a vertical structure. On the left-hand side, we see the way different elements of BIM. At the lowest level, you have the three-dimensional CAD. And then a little bit higher than that is an intelligent model. And higher than that, it has information management. And this is the technical part. But if you use it for collaboration, so you can develop the model and collaborate, then that means it has to be through a network. So you have to synchronize collaboration, and then you have to have coordinated work practices. And then you have to also have some institutional and cultural framework that would allow for collaboration through digital model. The pandemic has pushed these things. So digital transformation has become much more prevalent due to the unfortunate, the pandemic of COVID-19. And we can see it in terms of having this meeting, that we are collaborating digitally in the sense of having a conference, but also in many aspects of life, and also in companies utilizing these things, these tools, more and more. SIM, of course, is digital transformation at the enterprise level, which impacts all of the operation, not only design and project delivery, but also other aspects of the operation within any company or organization. But let's take a few minutes and look at how the trends in digitization, visualization, and modeling capabilities have evolved over the years. If you look at the early days, we had GIS, computer mapping, and manual drafting, some level of GIS maybe, perspectives, and then GIS and 3D dimension came later on. Then GPS became commercialized. It became public. Public use of it became toward the end of the 80s. And then that created a lot of opportunities. And then desktop mapping became available. Then network mapping and wireless technology became available in the 2000s. And then, of course, Google introduced the KML viewer and Google Earth. And then BIM started to evolve and be developed. And then as we are getting beyond 2010, BIM for infrastructure is getting developed. And I think the future is for digital twin technology. And already some companies, for example, for some other applications, they are trying to use digital twin for applications in manufacturing and other places. And I think for infrastructure, digital twins are becoming a reality currently and also into the next few years. So let me now go back a little bit and give you a little bit of background in terms of my experience with it. So about 18 years ago or so, maybe 20 years ago, there was a problem in California in which you can see on the left-hand side that you see this big truck going under a highway underpass and it's getting stuck, although the bridge heights are clearly indicated, but the bridge heights can vary during the span of the bridge or underpass. So the issue was, how can we have a continuous measurements of the bridge heights or underpasses throughout California, and how can we do this in a cheap way? And at that time, laser scanning devices commercially were not available the way it is right now. So what we did, you can see here in the middle, we took a rotating mirror and a small laser system that you can see in this box. And then the laser would shine through this rotating mirror. And then we put an optical encoder on it so we could measure the number of revolution. And then we integrated the GPS, you can see on the top here. And we put this thing on a simple structure which had on a trailer hitch. So we can go in, we took a car, which is just a regular SUV with a trailer hitch. So we could connect through the trailer hitch to it. And then we had a processor that we could measure, and we could tag the measurements with GPS and a dead reckoning system connected to the car, so that we would be able to know, tag it exactly on the highway as we could go. And we could go at 50 miles an hour. And you can see on the left side that we could get a digital image of the underpass. So because the car is moving and the laser scanner starts, this is like a simple laser scanner, you could see we would get these laser scans that as the car is moving, it's just going to go like a cylindrical laser scan of anywhere on the highway. So we could get bridge height inspections very easily, and we could do this very easily for everyone in California driving at highway speeds. Then the next step was we realized that, hey, with this, we now have a lot of digital data, so we can perform a digitization of highway infrastructure. And as we were doing these things, then commercial laser scanners were becoming available. So you can see here, there was a section of the bridge that goes to Oakland that got, because of some fire that occurred, because of a truck that had an accident and caused a fire that collapsed. So we went there and we did a digital scan right away. And later on, when they were building when they had a contractor that was going to perform the alignments, and the transportation agency wanted to check the alignments, then we went with our scanner and we scanned and we checked their alignment data to make sure that they are going to do it correctly. And then, of course, for underground things, we have used ground penetrating radar. And these are the piers that are going to be put into water. And you can see on the right-hand side that are digital view of what is underground from our ground penetrating radar. And then all of these things can also use for construction. So you can perform, and I'm sure you guys are familiar with it. So you can use laser scan and use it for machine guidance to guide operations for grading and things like that. Then there was a contractor that was going to be building the new Bay Bridge that connects the East Bay to San Francisco, the east portion of the Bay Bridge. And what we did, we also used our scanner. We did a laser scan for alignment and also for other purposes. And then later on, I'm going to show you this video. This is driving through the Bay Bridge and scanning it. So this is a laser scan of the Bay Bridge. The east section of it. Another project we did was, there was a bridge called Antler Bridge. And here we use digital transformation in a different way. So there were contractors that were constructing the bridge, and to perform the inspection operation, so we had our laser scanner set up, and then the laser scan every day would scan, and we would be able to match the scan with the So the scan would show the progress. We would match it with the schedule. And then we would also match it to make sure that all of the tolerances are met. And then this way, at the end, we were also able to produce an as-built, the digital as-built of this bridge. So this is sort of like a reverse engineering aspect of it, or something that can be used during inspection to monitor the project delivery. So now that you got some examples of things that were done, let's look at the elements of digital transformation for horizontal construction, or elements of VDC and SIM. So we have information models that include, you need to have common data exchange environment, information standards, and there are some things that can help us, ISO, and then you can use, in some cases, XML, etc. But ISO provides a lot of data. Nowadays, they're very well advanced in terms of providing a lot of standards. You want to do a data dictionary, and then some templates for information model, and then some templates for electronic data and document management. And also, you have to standardize the information exchange. For the teams, you have to make sure you define the roles and responsibilities, methods of communication, how you synchronize collaboration, and then coordinate work practices, and then manage the stakeholders. At the enterprise, you have to develop governance methods. So you have to make sure that you impact the institutional and cultural framework, put policies and guidelines and the standards for adaptation, address legal and liability issues, and develop conventions. The process, you want to make project object-based parametric modeling, develop process workflows, and then do information management and project delivery. And then you want to take advantage of LiDAR, ground penetrating radar, GNSS, global positioning system, GIS, e-construction, e-signature, and so forth. And then you want to make sure you address your IT infrastructure. So you make sure you have data repositories for storage. You have to define methods of access, security, and then the bandwidths. This is the SIM diagram by FHWA that has at the core the enterprise or core data warehouse, and at the outset it has this GIS, use of drones, LiDAR, 3D engineering models, and so forth. And then in the middle layers has the finance, business operation, and then asset management, asset collection, and as-built plans, design, survey, planning. We modified this. I think that for our purposes, we made this into a larger thing. Still, data and document management is at the core. Business, we put the business operation just next to the real world. So the business operation has to be there because you need to define key performance indicators. And you need to worry about the finances as you're dealing at the outset. And then, of course, design is in the middle, is in the next layer. But then you also have to deal with contract administration. You have to deal with culverts, bridges, environmental factors. In California, you have to worry about, you have to collect water, for example. You cannot just let the water drain anywhere. You have to collect them and so forth. And then, of course, dealing with your data, you want to use GIS, LiDAR, UAVs, 2- and 3-dimensional, 5-dimensional modeling, and so forth. So we modified the FHWA diagram. I think that this is more representative. So the key points to keep in mind for the workflow in transformation of horizontal construction, you want to make sure that documents and data are at the center. SIM tools are on the inner ring. SIM activities are on the green ring. Here you can see on the green ring. Then project management is on the blue ring. And then asset management uses data from many of the activities. So asset management is something that is across and takes things from various activities. When you look at digital transformation, one of the questions that always an organization has is what is the ROI, the return on investment? And when we are trying to do this, we said, okay, let's look at ROI in BIM, because a lot of data is available for BIM. Less data is available for infrastructure, for highways or horizontal construction, but for buildings, there are a lot of data. So let's start there. So there are publications that did surveys at different countries for people who have used BIM, and you can see what the data shows. For example, in the United States, about 75% of contractors who built vertical structures said that BIM would have tremendous benefit for them, that has positive ROI. In Japan, close to 95%. In Germany, close to 95%. In France, close to 95%. Canada, more than 80%. Brazil, more than 80%. United Kingdom, about 60%. South Korea, about 50%. So this gives us an idea that BIM, in general, digital transformation does have benefit. If it has benefit in vertical construction, it has to have return on investment for horizontal. There are other ways to look at it too, from a theoretical point of view. There's this diagram that has become popular called McLeany's curve, which shows that when you do traditional construction, it shows with red curve here, a lot of the design changes, you see this curve that goes through, this is for design change. A lot of design changes occur at the time that you have generated your construction documents, or just before that. So therefore, there is a lot of cost associated with it. When you use BIM, because you're dealing with a virtual model, or when you use SIM, for example, when you're dealing with a virtual model, many of your design changes, not all of them, but many of them are handled at the time that you are dealing with this digital model. So there's the cost for design change is low. So you can see the curve here, that the ability to change is decreases as you're going to get toward construction. So if you can do your design changes here, that is going to give you savings in cost. So this is a theoretical curve that would theoretically show you that there is an ROI, or return on investment, when you use digital technology. This is another thing, data that can be used. NIST, which is National Institute of Standards and Technology, has done a study in manufacturing, and they have found that there's a estimated they have estimated the cost of interoperability. Interoperability comes when you have digital models. And when we apply that to the life cycle of design for horizontal construction, you can see that, for example, when you do preliminary design, the red line is the traditional and the black line is for beam or seam, that every time you do a change, you're going to cause some loss of information, and then as a result, an increase in cost inverse to that. But when you have a digital model, there's never a loss of information. So the information value increases, and as the information value increases, there's less chance of design changes, and therefore you would have a higher ROI. Finally, here are some data that exist on actual application of digital technologies to horizontal construction. You can see here the ROIs for different components. For example, for 3D modeling, tremendous cost saving. Mobile LiDAR, to some extent. So you can see these are return on investment. So return on investment, when I say to lesser extent, it still is a lot. So it's like 3 times. This is like 2.5 times as much for mobile LiDAR. For works on traffic analysis system, more than 3 times. Pre-construction assessment tool, more than 7 times. Electronic bidding and contract awards, 7 times. 7 times ROI is tremendous. This is 7 times of your investment. So there are different aspects of this. So now let's look at more details. So you have contractors, there's a process of bidding and construction, there's a process of design, you have to survey, you have to consider environment, project planners, you have to later perform maintenance operation and asset management, and of course you have to do construction. So we feel that data has to be common. So the common data should be used in all of these aspects. And if you have a digital model, if you have done all of your construction based on digital model and digital transformation, then you can achieve this. You can have a common data that can access all of these things. So as is model or as built model, survey model uses the same data as your 3D CAD, as your bid information is from the same data. Supplier for just in time, use the same data. Construction site, logistic for lean construction can use the same data. You can achieve all of these things. And all of this data is connected to geospatial. So you can perform all of the operations from the same common data. And then of course, if you have an organization, every organization have legacy systems. You have systems that you have already invested money in. So there's a question of how can I develop my data infrastructure so that I would be able to include my legacy system. And there are different ways, and the way that we recommend is to use a federated data structure. That's what I recommend, because if it's a federated data structure, you can include all of your legacy systems and still utilize them. Now, one of the things we did here for Caltrans, because you can have contractors and others who do, they get a contract and they do digital scan or digital survey of a section of a roadway. And then Caltrans, for California highways, they have these post-mile markers and so forth. So what we did, we developed in our center called HMCT, standing for Advanced Highway Maintenance and Construction Technology Center. We developed a software package called the LiDAR crawl. So meaning using LiDAR or laser scanner, we can crawl the highways. And we put that into a database, and that is connected to a GIS system, and our LiDAR crawl is synchronized with the post-mile marker. So then we can use this, we can develop, we can connect to web services, different web services, Esri, desktop, any local server we can connect to through a GUI, through internal web, because some organizations, some contractors use internal web. We can generate GIS analysis reports, and then we can, through a GUI, also connect to a public website, public-facing website. So even public can go in and see the status of a project and things like that. Now, if you have an organization, the question is, what would be the best methodology to try to integrate or to perform digital transformation of my organization? So we develop a methodology, we're trying to publish a paper on it. This methodology consists of at least 5 steps. The first step in your organization, if you're interested to transform your organization, so if you're a contractor or if you are a transportation agency, is to establish the baseline state of digital tools and technologies within your organization. And how can you do that? You can do that through developing a survey, and I can show you what we did, for example, for one organization. Then you need to develop a method that you would be able to measure or quantify the effect of incremental change. Don't try at the beginning to do a complete transformation. It may be very costly and it may take a long time. So you have to look at incremental change first and quantify, be able to quantify the effect of it. Because if you cannot quantify it, you cannot get your management to give you the resources and the funding needed to do the next step. You need to also look, when you trying to look at a pilot project to implement, you need to look at ease of application. You need to be able to calculate the effort needed to apply one of these digital tools or technologies. You also need to look at the financial impact. How much, what is the cost value? What is the value to do that? Or how much would it cost? So that you will be able to properly budget it. And then last but not the least, you need to look at other barriers. There might be organizational or legal barriers or other barriers. You need to look at them. And now I want to look at each of these things and tell you more detail of how we can do each of these. I think I'm running out of time maybe. So when you develop a baseline, a survey, you develop a rubric. The rubric, you would describe the level by 6 levels in terms of infrastructure. So if you want to take a tool and implement it, see if you have the infrastructure. If you don't have it, you put 0. If you have it fully integrated, you put 5. Training, is training available? Data sharing available? Method of data storage available? Then you can rank them. You can have people rank them. And then this is examples of ranking. Let's just go faster through these things. Then to quantify the effect of incremental change, there are tools like multi-attribute utility theory. So you can use utility functions and so forth. I'm not going to go through details because I think I'm running out of time, because I want to have time for questions and answers. And then for ease of application, we took advantage of technology readiness levels. These were developed by NASA, has been used by NIST and others. So you can use them, and we have defined different levels for them for horizontal construction. And then, of course, you have to evaluate monetary values, budget priorities. You can then consider the ROI. And then for organizational barriers, we consider both policy and legal. And then you can do something like the TRL, technology readiness level. And then we develop these things that call not allowed or illegal, requires a special permission, some restriction, minimal restriction, no restriction. So that way you can score them, and then that way you can decide what are the low-hanging fruits so you can implement. Let me go back. So for Caltrans, we developed a roadmap that you can see here. You cannot read it, it's very involved. But I want to take a few minutes to talk about other impacts of digital transformation. If you can digitally transform your horizontal construction, you can also impact the future of mobility, because you can then use the data for digital mapping that would impact autonomous driving that is becoming more popular. You can add digital connectivity, digital networks, so you can do update of roadways and traffic, so you can enhance driving experiences. You can also impact increased diversity in mobility, because then you can have demand usage for transportation units, enable innovation in on-demand mobility system, increase the use of transit as compared to individual vehicles, because you have digital data related to your highway infrastructure. We did that, for example, we did an example. We developed autonomous blowers, snow blowers, to open some roads in the Yosemite area, which they get about 50 feet of snow in the winter, and so forth. We have also some publication for those of you who are interested in technical aspect that are related to some of these, and we're trying to make other ones. But I want to also spend maybe 2 minutes on the future. So of course, one is application of digital twin technology. I don't want to go through this example, but I have talked about that. And then application of AI. For example, I took these things from a German asphalt pavement distress data set that is available, is open source. And then you can use AI, for example, to evaluate your pavement. If you have digital data about your pavement, you can use the application of artificial intelligence to evaluate them and then decide when the pavements have to be restored. I was just showing you, for example, you can use CNN, convolutional neural networks, different layers of, and we have done that on some applications for pothole filling and things like that. In your contracting, you can also try to take advantage of blockchain technology. And blockchain technology can have other applications too. So, you can think about using blockchain technology. With that, I'd like to stop and see, oh, I was going to show you, maybe I can show you, digital enhanced mobility in use of autonomous driving, also in use of drones for various applications. Oops. I think I have a video here to show. Oh. Maybe not. Maybe the video is not loading. I was just going to show you use of drone for bridge inspection. Using laser scan, using point cloud data, we have developed a technique that you can use drones for bridge inspections. So with that, I'd like to stop and see if there are any questions.
Thank you very much, Professor Ravani. This is very nice talk. So now we just open to the audience for asking questions. You want to go ahead and direct ask, or okay? One question here is that about the 3D data. So what are the 3D data used for? If you have other academic reports or papers for this, please help me. So this is one question.
So the three-dimensional data is used, for example, for design now, because when you look at horizontal construction, you also have to worry about roadside features that are three-dimensional. There are things that are inserted underground. If you have bridges, for example, you may have things that are under the road surface for handling water, for example, because you have to manage drainage. There are other also areas that you would have, you would reinforce the concrete so that you have to have data about that. You may have electricity wires underneath because you may have signs that have lighting on them. So you want to be able to, so you have to have three-dimensional data of all of these things.
Okay, thank you. Ben, you like to ask a question?
Yeah, thank you. Can you please maybe just go back to the slide where you were showing in the early part of your presentation the GPS and the dead reckoning system you had on the vehicle? You were doing bridge measurements. I was just interested how the GPS worked. I think you may have answered the question. The GPS, like, you know, when you go into the bridge, obviously you've got no GPS signal, but I guess that's where you then let the dead reckoning take over temporarily until you emerge from the other side of the bridge here. Yeah.
Yeah, so we have a dead reckoning. We have an IMU, integrated measurement unit, that has a dead reckoning system in it. So when you're under, that takes over.
Yeah, thank you. That's great.
And
what I
then
thought.
the other thing is, you have bridges that are longer. You can put these theodolites, and they can send signals like the GPS satellite signals.
How good is the GPS actually in terms of the positioning, accuracy these days? Is it better when you're traveling versus when you're stationary? Because
we have managed with mobile laser scanning, we can get it to be highly accurate to within centimeters.
And in the context of tunnel geometry, that's good enough uncertainty level for your centimeters.
And of course, if you need to have millimeter accuracy, then you can use multiple laser scans and so forth and improve the accuracy.
Yeah,
or you can,
cool.
but we have also developed techniques for putting control points and control lines, which are survey points, survey lines. And then the question is, based on the accuracy requirement, we have a chart that would enable you to know for what accuracy, how many survey points you need.
Yeah.
So the spacing of the survey points or survey lines would determine the accuracy. So we have developed data on that. We are developing now a facility on a highway near Davis, in which we are going to use for calibration to fine tune that.
Yeah, that'd be nice to see. Thank you.
Sure.
Okay, thank you, Ben. And one question here is about is related to the efficiency of find out the roadside parking spaces in the city. Considering a 2-lane road and 1 lane is allocated as a parking zone, how can we identify the occupancy of the parking slot digitally without having a physical sensor on the parking slot?
So you can also use laser scans to determine how many vehicles are in the parking lot. And if you're interested to read license plate numbers, then you have to have a physical vehicle there with a scanner on it that you can scan. Because if you are, for example, from a location outside the parking lot, if you scan, if the license plates are not in the direction of the scan, you cannot read them.
Okay, thank you. And one more question here is about using drones for bridge structural inspection. So what can you achieve for now, and what are the open challenges?
There are many open challenges. For one thing is to be able to get approval to fly near a bridge, because the flight zones, at least in the United States, there are specific areas that you can fly drones. You cannot fly them everywhere. And many bridges are in areas that you cannot fly drones. Now, if you have a road closure, then you can fly drones near the bridge. So if you close, for example, the bridge during an operation, then you can fly drones. Now, on bridges that are on certain areas on waterways where there's not enough traffic on the waterways, you can maybe fly drones near them. All of this requires special permissions and so forth. But one of the biggest challenges is that be able to fly drones near the structure without having a pilot, to be able to have, like, this is one of the things we were trying to do, to have a laser scan and then use the point cloud data. From the point cloud data, you develop the trajectory for the drone to follow to perform certain inspection function. So that's an open question for research. We did it at an elementary way, but even just doing that was the first step. But now more details of how you want to go to different areas of the bridge and inspect from the point cloud data.
This is more challenging, particularly on the freeway. The vehicle speed are very high. So, yeah.
But there's also, so if you want to do it on a freeway and there are cars, it's more difficult. I mean, you have to get permission. It's not easy to get permission in California because there's also distraction that drivers may notice the drone and then as a result get distracted and you have an accident and then all these things.
Yeah. So the next question is about NDT sensing. So is there any application of it in digital transformation?
I'm sorry, I missed it. What kind of sensing?
The NDT, non-destructive technology. Is that right? NDT.
Non-destructive testing can be used for bridge, it's used for bridge structures. And so, for example, eddy current or other kinds. But so the question is that how can we digitize that inspection process? I don't understand. How does that question relate to digital construction?
Okay.
I think what they're trying to say is how you can integrate, whether you can integrate that information into the BIM, just like you do with point clouds, for instance, whether there's any difference in that.
I see. So you can, if you put, for example, you know, one of the things in California, on some bridges, there would be some movement of the bridges, sometimes because of earthquakes or other reasons. And then the issue was, you know, the issue was that can we put sensors, and then if the sensors are connected to wireless network, so we would be able to measure them remotely. And this has been done, and we have done it. But also there's a lot of effort that is done on health monitoring of bridges. And if you have all these sensors connected to a sensor network, and then from the network you can have a wireless, then you would be able to have everything done digitally and also remotely. We also did put some sensors on some highway barriers, and then we sort of we had a remote way of monitoring when there was some impact to them. because sometimes some impacts were nuisance impact, meaning a small impact, and then the cars would go, but then we had to go and retract them because they were retractable. But if we didn't know it, we wouldn't. If Caltrans didn't know it, for example, or Department of Transportation would not know it, they wouldn't know to go and retract it. So we put sensors on them, and then through wireless networks, we would be able to detect it.
Okay, due to the time constraint, so thank you so much, Professor Ravani. It's really very interesting talk. Thank you so much.
Thank you. Thanks for the opportunity to give this talk.
Yeah, thank you. Thank you. Take care.
Yeah.
Thank you.
Thank you.
Okay, so the next talk will be given by distinguished Professor